All right, level 2, number 6. So here we have a roller coaster. So the roller coaster is going to go through a loop. So let's draw the loop. There's the loop, the loop, the loop. So the roller coaster here at the bottom is going to be zipping along. And of course, it's going to have to be going pretty fast, right, to make it around the loop. And they're asking us, what is the speed you would need to make it around the loop? And the loop has a radius of 15 meters. Well, the first thing we can determine is that means that the height of the loop is 30 meters, isn't it? Because the radius is half of the circle. So we have a roller coaster car, and we want to get it from the bottom to the top. So if we think about energy, we have a position 1 at the bottom and a position 2 at the top. And we know that the law of conservation of energy says that the energy in both positions is equal. So we start with that. And of course, when we do this, we have to consider the EK in position 1 and the EG in position 1, and the EK in position 2 and the EG in position 2. Now, if we look at this particular question, we can make some simplifications. At position 1, there is no height. You're at the bottom, so we don't need this term because there's no EG. There's no gravitational energy when your height is 0. If we imagine this roller coaster making it around the loop, well, you got to think about how fast it would have to go. If it went too slow, it would go up like this and fall back down. And if it went really fast, it would zing around the loop, no problem. So somewhere in between, there's a speed where it zings, it comes around the loop, and it just gets to the top and just about stops to 0. And then the gravity is enough to drag it back down around the loop. And that would be the minimum possible speed, right? That would be the slowest you could go. So you'd get right to the top where you would stop. So your V2 would be 0 at the top, and then you would stop for an instantaneous moment. But because you're at the top of the circle, then the gravity would be able to drag you back down around the other side, and it would work. So our V2 is 0, which means we have no EK at the top. And then we can do this conservation of energy equation nice and simple, and we can write in 1/2 mv squared equals mgh in position 2. We know the height at position 2 is 30 meters, so we can put that in here. We can cancel out the m's on both sides. We don't need the mass. And we know the g, and we can solve this for v1 to get the speed that you would need. That's how you